What makes things fall? What is this invisible force that constantly tugs at everything around us, pulling it towards the earth? It's a question so simple a child might ask it, gazing up at the sky with wide, inquisitive eyes. Yet within that innocent query lies one of the deepest mysteries of the cosmos, a puzzle that has captivated scientists and philosophers for centuries. You hold a stone, feel its weight in your palm, open your fingers and it plummets to the ground. Why? What is the underlying mechanism that dictates this seemingly simple action? This unseen influence is gravity, a force that permeates every corner of existence. It's the silent architect of our universe, shaping the grand structures we observe in the cosmos. Gravity shapes everything, from the smallest particles to the largest galaxies, from the arc of a thrown ball, the trajectory of a rocket, to the dance of galaxies, the swirling patterns of nebulae. It dictates how we move, how we interact with the world around us, how we build the very foundations of our cities and civilizations. Even the structure of our bodies, the way our bones and muscles are arranged. Without gravity, there would be no up or down, no order, only chaos, a swirling maelstrom of particles and energy. Imagine a universe where planets don't orbit stars, adrift in the vast emptiness of space, where stars can't form, their fiery birth stifled by the lack of gravitational collapse. Gravity brings order to this chaos, sculpting the cosmos into the beautiful and intricate tapestry we observe. The quest to understand gravity, to unravel its secrets, has driven some of the greatest minds in history, from Newton to Einstein. Why does the Earth orbit the Sun, locked in an eternal dance? Why do we feel weight, that constant pressure that grounds us to the Earth? These are all gravity's work, manifestations of its pervasive influence. So, as we explore gravity, remember that falling stone, that seemingly insignificant event. Its drop echoes cosmic events across the universe, from the collapse of stars to the formation of black holes. The story of gravity is the story of our universe, a tale of attraction, motion, and cosmic evolution. It's filled with breathtaking discoveries, moments of profound insight that have reshaped our understanding of the cosmos, and enduring mysteries, questions that continue to challenge our intellect and inspire our curiosity. Let's delve into what we know, and what remains tantalizingly unknown as we embark on a journey to explore the force that shapes our universe. The year is 1666, a time of great change and intellectual ferment. The world was on the cusp of a scientific revolution, and in the quiet English countryside, the seeds of a new understanding were about to be sown. Isaac Newton, in his garden, a sanctuary of thought and observation, sees an apple fall. It wasn't just the falling apple, but the way it fell that captured his attention. For Newton, this simple event sparks a profound idea, a moment of clarity that would reshape our understanding of the universe. It was a spark that ignited a flame of inquiry in his brilliant mind. Could the force pulling the apple also hold the moon in orbit? A question that bridged the terrestrial and the celestial. Was there a single, unifying principle at play? Before Newton, the heavens and earth were thought to follow different rules, governed by separate and distinct forces. The celestial realm was seen as perfect and unchanging, while the terrestrial was subject to decay and imperfection. Newton proposed a universal law, a revolutionary concept that defied the established order. Every particle attracts every other particle, regardless of size or location. From the smallest atom to the largest star, everything is connected by this invisible force. The sun pulls on the Earth, dictating its orbit and shaping our seasons. The Earth pulls on the moon, keeping it in its celestial dance around our planet. And even you pull on the Earth, a tiny but real connection to the planet beneath your feet. This mutual attraction is the secret behind the cosmic dance, the elegant choreography of planets and stars. Newton's law states that gravity depends on mass and distance, the fundamental ingredients of this universal force. The more massive, the stronger the pull; the farther apart, the weaker the connection. Specifically, gravity weakens with the square of the distance, a relationship known as the inverse square law. This elegant equation explained everything from falling apples, a simple demonstration of a universal principle, to planetary orbits, the grand celestial ballet of our solar system. Newton's law unified the heavens and earth, demonstrating that the same force governs both the mundane and the magnificent. allowing astronomers to predict planetary motion and discover new worlds, expanding our understanding of the cosmos. For over 2 centuries, Newton's vision reigned supreme, shaping our understanding of the universe and inspiring generations of scientists. It seemed the mystery of falling objects and cosmic order was solved, a complete and satisfying explanation of gravity's role in the universe. But science is never finished. It's a continuous journey of exploration and discovery. Every great theory has its limits, boundaries beyond which it can no longer accurately describe the universe. Subtle anomalies and deeper questions remained, hinting at a more complex reality beyond Newton's elegant framework. Newton's gravity was powerful, but not the final word, a stepping stone on the path to a deeper understanding. The stage was set for a new revolution, a paradigm shift that would challenge our fundamental assumptions about gravity and the universe. Newton's law explained the universe for over 2 centuries, but tiny cracks appeared. Mercury's orbit didn't match Newton's predictions. It shifted slightly faster than expected. This small, persistent anomaly hinted at a deeper truth. Newton's theory also implied gravity acted instantly across space, a concept that troubled even Newton. How could one object influence another instantly, with nothing in between? These puzzles suggested gravity was more than just a force. Perhaps it was woven into the fabric of reality itself. The universe was ready for a new idea. Now let's turn our attention to one of the most brilliant minds in history. Enter Albert Einstein, a name synonymous with genius and a figure who would forever alter our understanding of the universe. Einstein, with his revolutionary thinking, began to question the established laws of physics. Einstein realized Newton's gravity clashed with his own principle, a principle that would become a cornerstone of modern physics. At the heart of Einstein's thinking was a profound realization: nothing travels faster than light. This seemingly simple statement had enormous implications, shaking the very foundations of Newtonian physics. This led to his general theory of relativity, a groundbreaking theory that redefined gravity and our understanding of space and time. It was more than just an adjustment to existing ideas, it was a new vision of gravity. Where Newton saw gravity as a force acting at a distance, Einstein saw gravity not as a force, but as something far more fundamental. He envisioned it, but as the warping of space-time by mass and energy. To help visualize this mind-bending concept, picture space-time as a trampoline. Now imagine a heavy object creates a dip, and then smaller objects follow the curve. In our solar system, planets orbit the sun not because of a pull, but because they follow the curves in space-time. This idea explained Mercury's orbit and revealed something even more astonishing: that time itself is affected by gravity. According to Einstein's theory, clocks run slower in stronger gravitational fields, a prediction of fact confirmed by atomic clocks. In fact, your feet are slightly younger than your head simply because they're closer to Earth's center. With his theory, Einstein transformed gravity from a simple pull to a dynamic interplay between matter, space, and time. In essence, gravity became a feature of the universe's geometry. And with this new understanding, the cosmos would never look the same. Einstein's theory predicted something extraordinary: gravitational waves. Imagine massive objects colliding like black holes, sending ripples through space-time itself. For decades, these waves were only theoretical. Their effects are unimaginably tiny. Scientists built LIGO, a detector using lasers and mirrors kilometers apart, to catch these ripples. In 2015, LIGO detected the chirp of 2 black holes merging over 1 billion light-years away. The energy released was immense, confirming Einstein's prediction and opening a new era: gravitational wave astronomy. Gravitational waves let us hear cosmic events invisible to telescopes, like black hole mergers. They're not light, but vibrations in space-time itself. This new window lets us probe the universe's most violent and hidden moments. We can now listen to the universe's own song. Gravitational waves are a new language of discovery. The cosmos is speaking, and we're finally learning to listen. The universe's secrets are closer than ever. Gravity's effects are felt every day on Earth. The moon's gravity causes ocean tides, bulges of water that move as Earth rotates. The sun also plays a role, but less so due to its distance. Gravity holds our atmosphere in place, making life possible. Mars, with weaker gravity, lost much of its air. Gravity even helps us find oil and minerals. Tiny variations reveal hidden structures underground. Earth's gravity isn't perfectly uniform. You weigh slightly less at the equator than at the poles. Even on our own planet, gravity's grip has subtle nuances. Gravity does more than pull, it bends light itself. During a 1919 eclipse, starlight passing near the sun was seen to curve, confirming Einstein's prediction. This effect, gravitational lensing, lets us see distant galaxies magnified by massive objects. At gravity's extreme are black holes, regions where nothing, not even light, escapes. We detect black holes by their gravitational influence and now by the waves they create when they merge. Even on Earth, gravity varies, like around Hudson Bay, where it's slightly weaker due to ancient glaciers and mantle currents. Astronauts in orbit aren't free from gravity, they're in constant free fall, creating weightlessness. Gravity's wonders stretch from the everyday to the truly bizarre. We've journeyed from Newton's apple to Einstein's curved space-time, from tides to gravitational waves. General relativity explains the universe on large scales, but there's a problem. It doesn't mesh with quantum mechanics, the theory of the very small. When we try to combine them, like at black hole centers or the Big Bang, the math breaks down. This is one of physics' biggest unsolved puzzles. Scientists seek a theory of quantum gravity, a framework uniting gravity with quantum rules. String theory and loop quantum gravity are two leading ideas, imagining the universe as vibrating strings or quantized space-time. These theories are complex, but they represent our best attempts to bridge the gap. Solving this could reveal what happens inside black holes and at the universe's birth. The quest for quantum gravity is a search for the ultimate theory, a theory of everything. Gravity's story is far from finished. So what is gravity? We began with a simple question about falling. We saw Newton's law of universal pull, then Einstein's vision of curved space-time. We've listened to gravitational waves and explored gravity's influence on Earth. Gravity is a cornerstone of reality, yet it remains mysterious, resisting unification with quantum physics. The quest for quantum gravity is a drive to understand existence itself. Each discovery opens new vistas and new puzzles. Gravity pulls us down, but also pulls our minds upward, inspiring us to explore. It shapes galaxies, ignites stars, and orchestrates the cosmic ballet. The story of gravity is ongoing, a grand puzzle, always inviting us to wonder. In this vast universe, gravity's mystery is what makes it so amazing.